Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at dataengineeringpodcast.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your data pipelines or trying out the tools you hear about on the show. Continuous delivery lets you get new features in front of your users as fast as possible without introducing bugs or breaking production, and GoCD is the open source platform made by the people at ThoughtWorks who wrote the book about it. Go to dataengineeringpodcast.com/GoCD to download and launch it today. Enterprise add-ons and professional support are available for added peace of mind. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. You can help support the show by checking out the Patreon page, which is linked from the site. To help other people find the show, you can leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host is Tobias Macey, and today I'm interviewing Sean T. Allen about Wallaroo, a framework for building and operating stateful data applications at scale. So, Sean, could you start by introducing yourself?
Yeah, hi. My name's Sean Allen. I always go by the T. If you Google just Sean Allen by itself, there you can see the reason why for that. I'm the VP of Engineering at Wallaroo Labs. We make Wallaroo. I think you gave a good intro to what it is. And I also I spend time now as a member of the Pony core team. It's a language that I believe we're going to talk a little bit about later on, probably. And I was also an author of a book from Manning called Storm Applied about the Apache Storm streaming framework.
And could you tell us a bit about how you got involved in the area of data engineering?
Well, I don't remember exactly. It's just like I've worked on back-end systems for most of my career, although I took a detour through doing back-end stuff for websites and everything for a long time. And somehow when I came back out of that, I was working on back-end stuff where it became more and more about the data that was being processed became more and more important. And then suddenly, apparently, I was in the area of data engineering. And what the exact steps were, I don't really know at this point.
And could you start by giving a description about what Wallaroo is and how the project got started?
So I think in a lot of ways, Wallaroo is we're building towards the tool that I always wanted to have when doing a lot of data processing jobs, where we would take various tools and we'd try to build these ad hoc solutions, and they would usually work most of the time when things were working correctly, but once there were failures, we'd start to have all sorts of weird data corruption stuff. So Wallaroo is it's a framework for building streaming data applications. Although we're really looking towards eventually being able to support like batch use cases as well. So you could think of it in the same kind of area where stuff like Apache Storm is, but where we wanted to solve some of the problems that we thought were really hard about building applications like that, where you need to be able to keep track of state. You want to be able to scale these things up and down and whatnot. And so Wallaroo, I mean, we provide like managed in-memory state. We allow you to take a cluster of machines, grow it up and down. We provide you an API, which is scale independent. It's one of the things that we are quite interested in. Where the API that you're writing to doesn't talk in any way about the number of machines that you're running on, the number of servers. You're just talking about the flow of data through it and what your data structures are and the operations that you do it on it, so that you can take the same code which runs on like your laptop on one process, and you could run it, on your laptop on 3 processes, or you can take that same code and put it out into production or testing, on 10 processes or whatever that might be without having to make any changes.
And based on the fact that it will sort of transparently shard your data across multiple nodes, it sounds like there's a particular set of application types that it works well with, as opposed to being able to just run, for instance, your run-of-the-mill web application using Django or Rails. So are there any sort of particular use cases that you are most directly targeting with Wallaroo?
So really, at this point, like back of office like data processing jobs, probably ones where latency might be a concern for you. That's certainly the area that we started in. When we originally started building it, we were looking at doing finance type applications for banks, like risk analysis and whatnot that needed to be done in real time. But we've moved off of that to more generally for just any type of data application where you're handling events as they happen in real time and want to be able to respond to them. So I mean, this could be ad bidding, for like ad network type stuff. This could be, in the finance space, it could be analyzing, what's going on in terms of market data and changing algorithms on the fly. We're working with a large infrastructure monitoring company to where they want to be able to, they're taking data in from their customers, and they want to be able to trigger alerts based on that. That's a very much a, hey, we have real time data flowing in. We want to keep some state around for it in order to be able to analyze it. Like maybe like what's the state of this server over the last 10 minutes or something to trigger alerts. Those are a couple of the types of use cases, but in general, it's, hey, I have a stream of events, and I want to be able to respond and take action on them in some kind of fashion.
And at the beginning, you mentioned that you're heavily involved with the Pony language, and when looking through the documentation, it's pretty readily obvious that that's the language that you use to implement Wallaroo. Before I started reading through the documentation, I don't think I had ever really seen mention of that language, so I'm wondering if you can just take some time to describe a bit about what it is and the features that it has that makes it well suited for the problem area that you're focusing on.
Yeah, so Pony is a fairly new high performance actor based language where the programming model and concurrency model is similar to like what you would see with Erlang or with Akka on the JVM. Those are both actor based, but it's really one of the things that it has, which is novel and different, is a type system, which is designed to allow you to do message passing in the same way that Erlang has in a safe fashion. But Erlang has some performance constraints where it copies most data which gets sent from one actor to another, which can be a bottleneck on performance. And Pony uses its type system to allow you to, like to say, do unsafe things in a safe way, where you can the compiler can guarantee that like memory is not being shared across multiple threads at one time, so that you don't have to do copies in order to make sure that things are safe. And when we were looking for something to write Wallaroo in, we had a series of constraints that we were looking at the time, where we very much wanted to have we wanted to be able to process high volumes of data. We wanted to be able to do it quickly, so we were already looking at performance type things as something we needed. And then we were also looking for, one of the things that we really wanted to have was, if you're doing stuff like we were looking at the beginning, like risk and financial applications and whatnot, then tail latencies could be a real concern. Like a lot of the folks that we were talking to, they were building applications where one of their problems was, that they had built this on the JVM, and they were struggling with JVM garbage collection, where a non-trivial amount of their requests, rather than finishing in the like couple of milliseconds that they needed them to finish in, there would be a GC pause, and it might take several hundred milliseconds or more for those requests to be processed. So we're also looking for a solution where any garbage collection or memory handling that might go on would be one where we'd have nice flat tail latencies. We looked at an awful lot of different things, and in the end decided to go with Pony, despite the fact that it was relatively young, and in large part because we thought that for the problem that we were solving, that the actor model would be a really good way for us to go about doing this and modeling our concurrency problems. Because we were really worried about, hey, okay, we're going to build this high-speed thing, and we want to make sure that we're not accidentally corrupting data that we're handling for the user. So we were like, the actor model was one that we were comfortable with, and then it started to be, okay, if we do the actor model and we decide that this is the route that we want to go, what are our options? We looked at Erlang, and we talked with some folks that we know who are using Erlang, and they're like, Erlang is great, but we don't think you're going to be able to push it the way that you're looking to. And we looked at other stuff like, well, we could do this in C, but we had worries about memory handling. We seriously considered Rust, which is further along than Pony was at the time. But that would have been, at that time, it would have been, hey, we're writing our own actor model. And Pony, while being a relatively new language, the runtime had been around for much longer. It had been used at one of the major banks in the UK. And we were like, well, if we did this in C, we'd probably end up writing a runtime that looks a lot like this. So let's go ahead. Let's start with this runtime. And let's build from there and become a part of the the community for this. We'll try it out. We'll see how it goes. And over the course of several months, a lot of the folks on the team at Wallaroo Labs, became members of like the Pony committers and whatnot. And everything worked out really well for us. And we've been really happy with the choice of language.
Have there been any instances where the lack of ecosystem has been a problem, or have the primitives within the language been largely sufficient for the type of work that you're using it for?
They've been largely sufficient up to this point. A lot of what we're doing is really much more low level type stuff where, because of the performance concerns and whatnot that we had, that taking off the shelf libraries and sticking them together probably wasn't going to work. Even if we'd used like a JVM based language, for example, we probably would have either ended up using like a few of the like high performance computing libraries that provide a number of like data structures which are more suited to high performance computing than what's in the Java standard library, or we would have ended up writing our own anyway. So while Pony is young and it has a small standard library, that didn't really bother us because we were gonna end up writing probably most everything for our early work anyway.
And would it be fair to describe Pony as a special purpose hybrid between Erlang and Rust in terms of the fact that it's oriented around an actor model but also has the memory safety guarantees?
If you wanted to do a 15-second elevator pitch to folks who knew what Erlang and Rust are, then yeah, I think that's a reasonable way to initially approach it.
And the user API for people who are using Wallaroo, at least at the current state and time, is via the Python language runtime. So I'm curious why you chose to focus first on Python as the language for interacting with Wallaroo and how you've built that integration for being able to embed the Python API within the Pony runtime.
So our first API was actually C++. And we still have a C++ API, but it's not one that we're actively supporting at this point in time. Although if somebody came along and said, hey, we really want to do a thing with C++, we'd happily pick up work on that and work with them. But I mean, what really happened was that the folks that we were going out and talking to who were showing interest in Wallaroo were using Python. And there are more and more people in the Python community who are looking to do real-time data processing, and there's just not a lot of tools that are there. I mean, if you go look, the Apache Software Foundation has an ungodly number of real-time tools to do processing if you're running on the JVM, which is great. It's awesome. You have a wide variety of choices. But if you're doing stuff with Python, you have a smaller set of them. And most of them that you have are probably going to require you to use the JVM. And there are a lot of shops they're primarily Python shops where, they recognize that while the JVM is an awesome piece of technology, it can also be operationally difficult to run in terms of tuning GC and whatnot in order to get optimal performance. So the folks who we seem to be appealing to were ones who were doing Python stuff but didn't want to take on like managing the JVM and whatnot. So that's really how the Python one came about for what our primary focus is right now. Although we have also had a lot of people in the same vein who are using Go, who we've been speaking to, and so we're currently working on a Go API as well. Because again, it's this same thing where there's just not a lot of tools for like real time like stream data processing within the Go ecosystem. But the question of how do we go about doing this with the Python? So what we have is you have Wallaroo is in some ways it's a Pony library, and what we do is we have a main entry point which is in Pony, and we embed at this point in time, it's a Python 2.7 interpreter, and we embed that inside of a Pony application, and you supply our runner application, which includes the embedded Python interpreter. You supply it a module which it would load, which is standard Python code, and it can use any libraries, any modules that you have installed within your normal Python environment. And so you could use virtual env to set up environment for it, or you could just use the stock Python, which is installed on your machine. And we use the Python C API to talk back and forth basically between the Pony code and the Python code over with a small bridge of C code, which is interfacing between Pony, which has excellent C FFI, and the Python C API, where we increment and decrement GC counts on objects as they come back and forth in and out from the user supplied code and whatnot. We call known Python methods that we're expecting to find in certain places and whatnot. All of this using the API that you would use to write Python modules in C, or call from C back into Python if you were embedding it for some type of game or whatnot. So we use that standard way of doing it, and then we're going to be doing that for Python 3 soon, which because that API is pretty much basically the same, should be really straightforward for us, because there's actually very little Python code that we have that's involved in it. It's pretty much we're doing all the interaction through C.
And one of the main promises of Wallaroo is the fact that it allows for easily distributing state across multiple machines. So I'm wondering how that works internally and how the internal architecture of Wallaroo has evolved from when you first started working on it.
So I think the internal architecture, for the most part, when it comes to handling of state, has been pretty much the same from the beginning. We did a lot of internal architecture changes which were related to getting better performance. Like the second version of Wallaroo that we ever did ran at maybe 1/100th of the speed that we currently have, but hey, it worked. And amusingly enough, the very first version of Wallaroo that we did was had 1/10, not even 1/10 of the features we have now. But we wrote it in Python in order to get our testing harness set up around it. But so there's a paper by Pat Helen called Beyond Distributed Transactions: An Apostate's View, and in it he talks about it from a database standpoint of how you could build a database that in theory could scale infinitely. And one of the ideas he talks about is that you would have these things, and he calls them entities. And these entities would be transactional boundaries where these entities are based on things in your domain. So like if you have like some sort of a system which is dealing with customers in your system, then each of these entities might be a customer, and you could have other entities that are for products, rather than operating on tables with relations in them. And then you could spread these entities around across an infinite number of machines. As long as you have enough entities to put on each machine, you could keep doing that. And we hadn't actually read that paper before we started building Wallaroo, but that basic idea of those entities matches up very well with the concept that we have that we called state objects, where the programmer writing their program can define these objects which represent whatever the state is for their particular domain, which is opaque to Wallaroo, but you provide those objects in your language, and you also provide how that data would be partitioned. So like in a lot of like classic word count examples that are done for streaming data, things are, it's usually like, hey, I'm going to break this up where I'm going to have these different buckets in order to parallelize based on like the first letter of a word or whatnot. So that's a fairly simplistic thing. But if you're writing word count in Wallaroo, and we have an example word count application where people can see this being done, is we do exactly that. We create a partition for each one of these, each of the letters of the alphabet, and in the application, and then Wallaroo will manage those. And so if you're running Wallaroo on one process, it's going to have like all of those data partitions in that one process. But if you start up, say, a second process and connect it to the first one, so you're now running with two processes, then you're going to have the state objects of which you had 26. They'll now be 13 on each machine. And in general, it's like as you add more processes, your state objects will be distributed out across that. And then underneath, what's actually happening with these is that each of these state objects is managed by an actor underneath the system. So there's no way that for any of your data objects, there's no way, because of how we built it with the actor model stuff underneath, that more than one thread could ever be concurrently accessing your particular bit of data, so that there's no way that you're going to ever have race conditions or whatnot where more than one thing is trying to update that data at a time. It means that that on each one of your state objects you'll end up serializing things, and there are also potentially, depending on how things work, there are certain ordering guarantees that we can provide based on that.
And when reading through the documentation, one of the things that you call out is the capability for promising exactly once processing, because of the fact that it guarantees at least once delivery and then idempotent processing of the computational state. So I'm wondering if you can just dig into that a little bit, and particularly in terms of how you ensure that exactly once processing.
Yeah, so we exactly once is a very overloaded term. So we like to talk about exactly once processing, which is that we definitely might end up delivering messages more than once inside of Wallaroo, but we have a work acknowledgement protocol which we can combine together with a write-ahead log that we use in order to save out state changes, so that if there's a failure when we bring stuff back, we can make sure that we're not going to process the same message twice within Wallaroo. And I think the within Wallaroo is a very important part of that, because within any system, if you're doing some type of exactly once processing like what we're talking about, is what you're really saying is you have at least once message delivery, which is if you don't get an acknowledgement that a message was sent and processed, that you can resend it. But if you just have at least once message delivery, that means that you can have duplicates, and you could process stuff more than one time, which means that whoever's on the receiving end of that has to be able to have some type of deduplication, or the operation has to be idempotent. Otherwise, you're going to end up with incorrect results. So once you're at the boundaries of Wallaroo, then we can't make that guarantee unless you're interfacing with another system, which can also make that guarantee. So like when you're sending your results out of Wallaroo system, if you are sending it using Kafka, for example, where Kafka has an idempotent producer, then you can continue to get exactly once semantics for your actual system as a whole. But if you were sending this out to over TCP or something like that to a receiver which was just taking stuff and writing it out to a file, for example, which does no deduplication, then you could end up with the same line appearing in your file more than once, because you're no longer talking about Wallaroo internal to Wallaroo, but you're talking about a larger system as well. So we definitely like to draw that distinction there of whether you're talking about inside Wallaroo as an application, or when you're talking about where it interfaces with external systems as part of a larger system as a whole.
And going back to the topic of the state management, is the state persisted in any way for longer periods of time, or do you only maintain it in memory and within that write-ahead log for long enough that the transaction can be completed, and then there's a cleanup phase to remove that particular piece of state?
So we don't currently have a way to expire state which is in memory. We've been talking to some folks who have use cases where it's more like they want to keep stuff in memory, but maybe only for 10 or 15 minutes, and then they want to have it expire. So currently, right now, when you create a state object, it's going to live forever in memory. But that idea of expiring ones is something that that we're looking at, and the right way to do that. And then you can either run in what we have a resilience mode and we have a non-resilience mode. If you're trying to get the absolute fastest performance that you can, you'd want to run in non-resilience mode, which means that all of your state is only in memory. And if you were to have a node crash, then there's nothing you can do to get it back, which, for some scenarios might be acceptable, where performance is more important to you than anything else. We also have a resilience mode, which right now involves taking any of those state changes and writing them out to a write-ahead log as they happen. A local write-ahead log, and then also writing out, as part of our acknowledgement protocol, how far along in the write-ahead log basically we've actually gotten to for work that's acknowledged, so that if you have a crash, you can come back to whatever the last acknowledged point was, and we can kick off our recovery protocol to replay messages which weren't acknowledged. So that's what you can do in terms of resilience for that. We've actively looking at, when you have a cluster of machines, replicating data from across different nodes in it, but right now the resilience strategy is to just use that local write-ahead log.
And in order to maintain performance when you are taking advantage of that distributed state capability, do you use some form of distributed hash table to ensure that messages are consistently delivered to the same set of nodes based on the certain prefixes that you care about for being able to split them out, so that you don't have to worry about any sort of coordination between nodes or synchronization of data between those nodes to ensure redundancy across them?
So everything that we strive to do based on the background is that we want to do everything based on local knowledge, not global knowledge, because global knowledge is a point of coordination, which is going to end up making things slower. So pretty much basically your application starts up and you're running on, say, just one process in order to make it simple, and you have, like in that word count example we talked about earlier, you have 26 state objects which you're managing. So we know we have knowledge which is built at the time that the application starts up for how you do routing for any of those 26 state objects. If you were to start up and you had two processes where the processes are talking to each other over TCP, then when it starts up, we know that there's there's 13 state objects on each of these particular machines, and we know how to route to them based on local knowledge at that particular point in time. If you were to change the size of the cluster, we have a period of time there where one state objects would have to be shuffled around to take advantage of the new cluster size, or shrink to the new cluster size. And at which point during that period of time, the layout and the routing gets reconfigured, where you effectively have one of the nodes become a leader for the deciding of where data will live, and then coordinating that it's all moved to the right place. But yeah, there's no global understanding of nothing looking down on where it is. It happens when the application starts up and when there's a change to the cluster size, and then otherwise at any of the points where you might route a message, we know where you're supposed to be routing it, because, well, actually one of our really early versions of Wallaroo, we had a per process object which was responsible for knowing where to route stuff, and that was our number one performance bottleneck. We had an application which was designed to see what the overhead was, that we were adding in. So it was trying to process large numbers of small messages that were mostly just shipping those small messages around while doing minimal processing with them. And we couldn't process more than probably 50,000 messages a second with our first version that we had, and it had this per process global routing registry. And when we removed that, we got a more than 10x improvement in speed just from removing that one bottleneck. And a lot of our work as we went along was, how do we take knowledge which is currently global and move it into local knowledge, and really okay, this is going to be there, so we have to put this here, and it'll always be there. And it leads to better performance and whatnot, but it can be a little trickier to follow along than if you just had a global object of hey, where do I route this? Oh, okay, you say to route it there, I'll route it there.
Beyond the considerations of trying to reduce the amount of global knowledge that's necessary, what have been some of the other more challenging aspects of building the Wallaroo platform?
We're talking about, we're building a system that allows you to run arbitrary user code with arbitrary user data objects in these applications that are going to have topologies of an unknown variety. So there's basically there's an infinite variety of ways that things could be strung together, and uh, that there's an awful lot of surface area there of stuff that you need to test to know that things work correctly. And I would say, that testing has more than anything else, like figuring out how do we go about testing things? How do we know that this is working correctly? I think we've spent it was performance, and it was testing and correctness, and how do we know these things are correct? And we invested more time in those two areas than anything else, and that's certainly been like, I mean, that's been a really big area. I mean, for us, I mean, and you look at it, there's an awful lot of stuff out there. There's like Kyle Kingsbury's Jepson work. There's stuff that Peter Alvaro did for lineage-driven fault injection. There's all the stuff that like the folks are doing with chaos engineering, a lot of which is come out of Netflix, of how do you take a distributed system and prove that that it's working, or in the case of chaos engineering, more of like, we think it'll be able to survive X type failure. And we have some tools that we built for ourselves in order to do this, but the amount of time it takes to build those tools, or to set up tests for those type of things, and then to be able to do it in a repeatable fashion, there's an awful lot of engineering effort that goes into that.
Yeah, it's sometimes shocking how little consideration organizations or engineering teams will put into the amount of effort and knowledge and skill that's necessary for proper testing of software in order to be able to ensure that it's as reliable as it needs to be for production use cases. All too often it's left as a last consideration that is given short shrift in the overall engineering budget.
Yeah, it's very hard. So like I touched on this briefly at the beginning, but the first thing we did, and we did this as how we were going to evaluate using Pony, was we created a really simple version of what we wanted Wallaroo to do, and we did that in Python, where you had Python processes that were communicating with each other over UDP. And we started to build testing framework tools in Pony around it, where we're like, okay, we'll try Pony out for this. And we started building a framework of tools for how do we know how do we know that we didn't drop messages? How do we know that we didn't duplicate messages? How do we know that if we sent into an application which is supposed to double a number, if we sent in 1, 2, 3, 4, and 5, that we got the correct results out the backside. And it was so we built these tools, and it became like that's where we tried out Pony. But it's also, we got at least a general framework for how we wanted to go about testing Wallaroo. And one of the decisions we made early on was that we realized that we were going to be spending an awful lot of time rewriting the guts of Wallaroo over and over again to facilitate better performance. And what the strategy that we really ended up with is the vast majority of our testing is end-to-end integration tests, where we run happy paths, and then we also we inject various errors into our runs, disconnecting nodes from one another and whatnot, in an attempt to make sure that we get correct results. And this is really effective for finding obvious bugs with the interaction between stuff. But it also comes at a cost of, you have a bug which might be the result of a timing issue between some number of nodes, which you might only see one out of 100 times or something like that. We actually fixed one today, which was, it only happened at the very beginning of when data was being sent, in just a specific timing at the beginning of an application starting up and whatnot. And our tools found it eventually, but that bug had probably been there for a long time. But we also don't know how else we would have found that. There's no unit test that would have found that, because everything technically at the unit level was doing the right thing. It was just that the interaction of stuff as they came together. So yeah, I mean, we put a lot of effort into that. I have a couple of talks. One that I gave at a QCon in 2016, and then I gave the same basic talk just updated like a few months later at CodeMesh in London, where we really talked about that. It was called "How Did I Get Here? Building Confidence in a Distributed Stream Processor." And, it's basically the talk is more or less a big love letter from me to Peter Alvaro and the inspiration that his lineage-driven fault injection paper gave us.
And which, if any, of the axes of the cap theorem have you optimized for, or is that something that's tunable for the person who deploys the infrastructure that underlies it?
We very much want it to be tunable. Right now, we are very much on the consistency side. Like if you lose a node right now, you have to bring the node back before we'll continue processing. When we add in replication of data across nodes, you'd be able to lose a node and continue processing because we can reroute to one of the replicas and whatnot. That can be a little tricky, but it was something we'd be able to do. And from there, we could also start to look at tunable consistency stuff. But we pretty much believe that if we're going to do some type of tunable consistency, that you'd no longer be able to use opaque data objects. Early on, our idea was that, hey, what we'll do is we'll provide data objects which you can build yours on top of. And that was very much like, hey, we'll provide CRDTs and whatnot, and you can do this and we'll have tunable consistency. But for most of the people we talked to in the beginning, it was, no, I want to be able to use my own code to define my own data types. But when it comes to tunable consistency in the future, we think we'd build that on top of replication and of data across nodes, and then using CRDTs, and have people be like, hey, if you want to take advantage of this, you need to be using CRDTs, which we'd build in.
And just to clarify for anyone who's not familiar with that acronym, CRDT is Consistent Replicated Data Type, which is a type of data structure that can be used in a distributed fashion without having to worry about locking or contention for being able to merge and process them.
Yeah. The idea behind CRDTs for folks who are listening is that I can have multiple copies of my data structure, which can be updated concurrently without having to coordinate with one another. And then there are rules that are built into the data structure for how you manage any conflicts that might exist. And you can pick different types of data structures where there are different rules for, like, a set or whatever, where if something was added and removed and you see both of those, well, should the thing still be in the set or should it not be in the set? That's a rule that's baked into the data structure itself. And there's a lot of interesting work that's out there on that. The Sync Free project, which is a European Union project, they got a lot of great stuff on it, as well as some stuff when work was done at Basho while they still existed. There's a lot of really interesting stuff in that space, and it's just starting to really make its way into industry over the last couple of years.
And for somebody who is convinced and wants to use Wallaroo as the foundation for their next project, what is involved in getting started and building an application on top of it?
So we're getting ready to release a new version next week where people will be able to pull a Docker-based environment which they can use, where everything will already be built for them for the Python stuff, and they'll be able to work with that. So you can go to our website, WallarooLabs.com, or you can go directly to the GitHub repo, which is github.com/Wallaroo Labs/Wallaroo, Wallaroo being WALLAROO. And there's links there to the documentation, which includes installation instructions on how to get started for setting up on either Ubuntu or OS X. You can for production type usage, you can use on any Linux system, but we wanted to provide instructions, for, hey, step by step how you do this for Ubuntu, because that's what most of the people we were talking to are using. The setup is not as simple as we would like. We have it set out where, hey, if you follow these directions, it should build just fine in Ubuntu, but we have the Docker stuff coming out where it can just be, hey, I'm going to Docker pull and all of this is set up for you. So there's a little bit of a hump there compared to just, I'm going to curl, a thing and it'll be installed, but we're working towards that. Then we have we right now what we really have is we have a lot of documentation about how you go about building Wallaroo applications, and we have a number of example applications that we walk you through, which demonstrate different parts of the API that you can go through and play around with. And then after that, it's like, hey, we have a mailing list that you can sign up for where you can ask questions. We have a IRC channel, and we're very happy to help people get started with whatever it is that they have. Most of us are time zone wise. We're either we're probably on the east coast of the U.S., but we have folks as far west as Vancouver and as far east as The Hague. So like if people stop by our IRC, then during business hours for one of those time zones, and it's quite possible that there'll be somebody there who can answer your question. If not, we have it all logged, and we answer any questions after the fact as well.
And in terms of deployment, what are the infrastructure considerations and resources that are necessary for being able to deploy the application to production? And then what are the scaling factors for being able to scale the application infrastructure out horizontally or vertically as is necessary?
For the Python stuff, you have the runner application, and then you also have your Python module, which you'd have where you've written the code for your application. So those need to be distributed together. Plus, you need to have a working Python environment there for any of the other libraries that you might need. So probably most folks would probably want to use something like a containerization on that. I would suspect, although you could also do it, where, hey, you're using something like a Puppet or Chef, and you have a standard way to install Python dependencies onto machines that you might already have. But certainly, this is a case where you need to, bundle up, some Python modules and everything else together in an application. Docker would be a good way to go about doing that, or some other container solution. Then, in terms of getting Wallaroo nodes to talk to one another, you can start up. Basically, right now, what happens is that it's like when you start up a new Wallaroo worker, you can tell it the address of another one that exists somewhere, and that will form a cluster with it, so that you could do this where you can say, hey, I'm starting up this application and I want there to be 5 nodes, and it'll wait until all 5 join. Or you can this isn't actually a released feature yet, but we have this thing that we call auto scale, where you're able to add and remove nodes from a running cluster. And then once that's in place, you can go ahead and you'd be able to change the number of nodes. It'll redistribute your state and whatnot. We have two means to get data into Wallaroo right now. One of those is Kafka. The other one is TCP. If you're using TCP, then you have a TCP connection which is open. You're pumping all your data in, and you'd be sending the data into that, and then it needs to be distributed out across the cluster. So network traffic into that, if you're using TCP, is going to end up being a consideration for how much you can scale. For the Kafka stuff that we have, currently the Kafka stuff has the same bottleneck, but we're in the process of making it so that as you change the size of a Kafka cluster, it will distribute out the partitions from a particular topic that it's reading from across however many workers you have, in order to be able to spread that out. So really, it's like, hey, you can add new workers to it as it's going along. It's a fairly simple and straightforward command line option in order to do that. And then beyond that, it's the how do you scale the data which is coming into your system and the data that's leaving your system, which in part depends on the type of source that you have.
And we've talked a bit about some of the failure modes that Wallaroo can find itself in, but are there any others that people should be guarding against in the application logic or the infrastructure architecture that they should be considering?
So I would say, like, in terms of in the application, no. Like that is if there's a problem there, then it's something that we need to address at the Wallaroo level. That's one of the big ideas of Wallaroo is that all of that nasty infrastructure plumbing that can take up so much time while you're building an application, right? Where hey, I could write word count that runs on my laptop in like an hour or so, but getting that so that I can run, like at Twitter scale where my word count becomes like, trending topics, that's the amount of infrastructure plumbing that goes into that is really huge. We want to put all of that infrastructure into the scale aware Wallaroo aspect so that you can write this scale, independent API. I think that the big one is, there's stuff like, people ask, have asked us is like, hey, can I do this across data centers? And, our statement right now is you probably could, but really we've designed this right now to work with, to have a cluster of stuff that works within a given data center. And if you wanted to do it across data centers, rather than setting it up as one cluster, you'd be probably much better off setting this up as clusters that are treated as independent applications that work together with each other in some fashion. I think that's like really the big one. Then Wallaroo is still definitely, it's still young. We have for the GitHub, we have a gotchas page, which includes like there's a number of failure scenarios right now that we're planning on addressing over the next 2 to 3 months, but that we don't right now. Where certainly, if somebody was to stick it into production right now immediately, we really don't think that anybody probably is going to usually. But if they were like to take it right now and put it into production, they should very much be aware of these gotchas, right? Where these are things that we're completely aware of and we're working on addressing. Like it's like, okay, like we can handle one failure of this sort, but if we have 3 nodes that fail all at once, our recovery protocols currently don't handle that correctly. Things like that we're working on.
And what are some of the situations or problem types that Wallaroo would be poorly suited for, where you would advise someone against choosing that as the implementation target?
Yeah, so I mean, right now we're very much about like event by event streaming data stuff, and a lot of problems that people don't think of as streaming problems can actually really are streaming data problems. But then there are some which just aren't. Like there are problems where you want to do like really large matrix math or something like that, that's not a streaming problem. That's suited to tools that are more like the HPC tools, that a lot of people were doing in the 90s, where they were putting together Beowulf clusters, or like Dask, for example, for Python. Has some stuff where it's good at handling stuff like that, and that's not in the wheelhouse for what Wallaroo does at this point in time. There's a whole segment of things that people consider batch type jobs, which are really streaming jobs. They just don't look like it, and those are ones that we're going to be adding support for in the future. And we have a blog post already of how you can simulate with Wallaroo what looks like a batch job for some type of stuff and whatnot. But really, it's right now it's like, hey, I need to do some type of like event by event processing. That's really Wallaroo's sweet spot right now. That could be, like, hey, we just started working with somebody where they're taking Twitter follower data that they have in files, and it's going to be shipped into Wallaroo, and they're building a graph of the relationships between them, and they're modeling that in it. And then when it's all finished and done, building that graph, all the files have been processed. We're going to send in another signal to it, which will cause it to output like the resulting graph. So like, that might sound like a batch job until you actually look at it and go, oh, hey, that is a streaming job. But yeah, certainly ones where you're doing like, you're trying to parallelize like matrix type operations or something like that, where you need to have like access to large segments of the data set and whatnot at a time. Not really a Wallaroo job.
And what are some of the most interesting or unexpected uses of Wallaroo that you've seen?
I can't really say that there's been an unexpected one so far. I think there have been a lot of things that we're talking to people about, which have been interesting, and are stuff that that didn't necessarily occur to us when when we first started building. Like there's a lot of ones where we talk to folks where it's really about, I want to have this stuff kept around in memory for a while, and I want to do it. Where in a lot of ways, what they're looking for, and this is something that we could provide with Wallaroo eventually, but we don't right now, is they're really looking for something like Redis, where they have like where they could distribute data structures around across a number of machines and run computations on those machines rather than having to pull the data structures back and forth, and then also still at the same time be able to expire those things at some point in the future. We've talked to more than a couple of people about that, and that's not actually very far from what Wallaroo does. Like the one big part of that would be the expire, but I never really thought it would be like, oh, hey, that's how people would be thinking of it. Which after I thought about it for a little bit, I was like, oh, well, that makes a lot of sense, because one of the reasons why we put this in-memory state in Wallaroo in the first place is that having to run external data stores for some applications can be a severe bottleneck, or can add operational overhead or whatnot. But the hey, we want this to be like where our data is short-lived rather than long-lived for the application. That one definitely took me by surprise. Is it wasn't really the type of use cases that we were thinking about really in the beginning.
Yeah, I can see situations where being able to set a TTL on a particular state object would be useful, because if you can't process it within that time horizon, then it's not worth bothering with after that point, because it's no longer useful information.
Yeah, I think like the first time we came across this was with the infrastructure monitoring company, and the use case there really is like that they're monitoring for alerts from customers, but not all of their customers are always sending in data, right? And the alerts are based on a time window like 5 minutes or 10 minutes or whatever. So if you haven't heard from the customer in like 10 minutes, and this is for it's supposed to be a 5-minute window, there's no point keeping their information around about what any of their alerts are. You can go ahead and drop that, and then when they might send in some data every now and then, you could go ahead and look up their information again, as compared to a lot of the stuff when we were first looking at this. It's like, hey, this is a continuous thing where it's really for one customer. And it's more of when we started talking to folks where this would be used to support many customers' data at one time. That's where really that sort of like, hey, we want to be able to expire this stuff, really started coming up a lot more.
And what are some of the things that you have planned for the future of Wallaroo that we haven't touched on yet?
We're working on a more Pythonic API for it, which we're planning on having out by the end of December. We have a Go API that we're working on. We have the auto scale functionality, which is dynamic cluster size that we're working on. We have a project where we want to be able to handle a wider variety of failures, where really right now it's like, if you have multiple failures that occur all at once, our recovery protocols won't necessarily handle those. So we have a project in GitHub for that. We also have the replication across nodes that we're really looking at, providing API support for making it easier to take those batch type jobs, which can be streaming jobs, and be able to do those. In a lot of ways, that would give you like there's like Flink does a lot of that, where it's like, hey, underneath this is a streaming thing, but we're going to give you a batch like API in order to work with it. Like those are some of the higher level ones. We also have some ones which are a bit more inside baseball, like the ability to dynamically add new partitions while it's running, which is one that would be really great. So like if you have a system where you're keeping track of customers, or even if you're counting words or whatever, to be able to not have to define ahead of time how many partitions you're going to have for your data, but simply say, I'm going to partition this by customer or by word, and if I haven't seen this word before, create this, put it somewhere in the cluster, and then go ahead and start routing data to it. That's going to be really powerful. It's going to allow for stuff to be scaled out more and make the API easier. We also have work around additional performance improvements for like the Python stuff, support for more sources and sinks. we're looking, quite seriously at, should we really like spend a lot of time doing a lot of integrations for, like all of AWS's stuff. An awful lot of people, who we're talking to or working with are running in AWS. So should we have, out of the box support for Kinesis and a lot of these other things? That's, some of the stuff we're looking at. But really, like right now it's new Python API, Go API, the auto scaling stuff are the big three. And then, a lot of work around the various failure modes, which we know that we don't fully support right now, and replication of data, so that you can have a fully replicated cluster.
And are there any other topics that we didn't talk about yet that you think we should bring up before we close out the show?
I'm sure once we're done, I'll think of some. But no, I feel like we did. We covered a decent amount of stuff. I'm sure by the time people have reached this point, there's already their brains are already a little like, oh, that was a lot of information. So no, I think we're probably pretty good.
And for anybody who wants to follow up with you and keep in touch with the work that you're doing, or ask any additional questions that we didn't cover here, I'll have you add your preferred contact information to the show notes. And with that, I'll ask you one parting question to give people something to think about. So from your perspective, what is the biggest gap in the tooling or technology that's available for data management today?
I think the biggest gap at this point is it's still too hard to do all of this stuff. There are a lot of tools that allow you to throw stuff together, but there's not a lot of tools that make it easy to do the hard things. I think we have a lot of things that make it easier to do easy things, but we need to spend more time investing in tools which might be a little harder to get started with, but will make like the hard problems much easier, which are issues around scale and data integrity and whatnot. And we have a lot of ideas with Wallaroo, and we've implemented some of them, and we have a lot more where we want to be part of that. I think there are a lot of other tools which they're all taking very different, interesting approaches to trying to solve different hard problems. And I think in the end, to me that's what's interesting about various tools, is what is the hard problem that I have that this tool is helping me solve. And I always have this idea that that no matter what you're going to build, there's the same amount of pain that's going to go into it. It's just a matter of where is the pain going to come. And I always like to look for what is the hard problem that I really have here, and what's the tool that's going to make that hard problem much easier for me, and then I'm willing to accept some level of additional complexity that might come along with that. Like for example, Haskell as a programming language has a type system which can provide, if you're using it, can provide an awful lot of confidence when you're doing refactorings and whatnot that you wouldn't necessarily get with a large code base with a language that doesn't have a type system like that. And right there, it's helping you solve what might be a hard problem for you, where you expect to have a large code base that you're going to need to be able to fearlessly refactor. But in return, what you're also doing is, you're accepting that there are fewer people who know this language, and that probably it's going to take you longer to get your programs to compile and whatnot. So I'm hoping for within, the data engineering space, that we have, that we continue building more tools which identify a difficult and hard problem that people would have, and provide solutions to that for folks who are willing to make the trade-offs that come with it.
All right. Well, thank you very much for taking the time out of your day to join me and tell me about the work that you're doing with Wallaroo. It's definitely a very interesting platform, and one that I may even find use for in my own work in the not too distant future. So thank you again for that, and I hope you enjoy the rest of your evening.
Thank you, Tobias. It was great fun.